In this video, I'm going to discuss locality and relativity as they pertain to spontaneous collapse theories. So with either one of the ontologies, so the matter density or flash ontologies, we can ask whether either version obeys locality, meaning no action at a distance. The answer quite simply is no, which we would expect given what experiments showing violations of Bell's inequality tell us. But how does this non-locality appear in GRW theory? So we can think about this in GRW matter density theory. We can think of an Einstein's boxes situation with two particles split between two pairs of half boxes. If we have Alice at x1 and Bob at x2 millions of kilometers away from each other, each with a particle split into half boxes, such that Alice has one in her left hand and one in her right hand, and Bob also has one in his left hand and one in his right hand, with the two particles in an entangled state that looks like this. So Bob has a measuring device that will point either left or right if his particle, we'll call it particle 2, is in his right or left half box. At t equals 0, Bob makes a measurement and finds his particle in the left box. Instantaneously, then, Alice's particle would also be in her left box. So right here, this is Bob's pointer. It goes to the left. We see that the matter was smeared out between the two boxes before time t equals 0. After he makes the measurement, it is definitely in box left. And simultaneously, Alice's will definitely go into her left-hand box. For the flash ontology, the analysis is similar, but instead of saying that upon Bob making a measurement, Alice's particle definitely coalesces into one of her boxes, it is just the case that upon Bob making a measurement, Alice's particle will definitely have a flash in one of her boxes if she herself makes a measurement. And so this tells us that we account for the non-locality of the GRW theories, which we would expect from violations of Bell's inequality. But can a GRW theory be made relativistic in the quantum field theory sense? And so for the rest of this video, I'm actually going to be taking from this paper right here. So this Allery 2022 paper where she discusses problems with the relativistic theories of the GRW theory. And so I'm going to be borrowing pretty much from this paper heavily for the rest of this video. It's a really good paper if you want to read it yourself. It's somewhat long, but it's quite readable. It doesn't have very much math in it, but unfortunately, it also doesn't have very many figures in it. So for the rest of this video, all the figures you'll see are figures that I myself made. They didn't come from the paper. So she says that people agree that non-relativistic quantum theories are in tension with relativity in the following respects. A, the dispersion relation, so the energy being equal to the momentum squared over 2m, which shows up in the Schrodinger equation, is non-relativistic. B, the wave function is a function of a single time, meaning that there is a absolute time. And C, there is a collapse of the wave function. The first problem can be overcome by having a Dirac or Klein-Gordon equation for the evolution of the wave function. The second point is an obstacle because the wave function somehow mediates the interaction and it is in configuration space. So it is not in actual, real, four-dimensional space-time, but is in configuration space. If the wave function describes arbitrarily distant systems with the very same time variable, then it suggests the existence of an absolute simultaneity. In other words, in order to make sense of claims like the following, what happens here now instantaneously influences what happens there now, one needs to be able to talk about the same now, here, and there. Nonetheless, this problem can be cured by introducing a multi-time wave function, which if you read the literature, some of which I have linked to in the references, they pretty much all do, in which there is a time variable for each system, each evolving according to its own equation of motion. Finally, the wave function collapse is instantaneous and therefore problematical from a relativistic point of view because it affects systems independently of their relative distance, thereby threatening locality. And so Allery 2022 discusses two ways of thinking about a theory of quantum mechanics being made relativistic. There seems to be two ways of understanding the spirit of relativity in addition to Lorentz invariance of the laws. Either locality of the interaction or preservation of the relativistic space-time structure. The relativistic GRW type theories are relativistic in the latter sense, meaning that they preserve the relativistic space-time structure, while relativistic pilot wave theories are relativistic in the former. So the pilot wave theories has a particle as part of its primitive ontology, meaning that it does have actual world lines, and so it has a sense of locality of interaction. So she goes on to say that Bell in 1987 noted that the flash ontology GRW theory was as relativistic invariant as it could be because it displayed relative time translation invariance. Two distant systems can get shifted in time by different amounts. GRWF is relative time translation invariant, while GRWM is not. And then later she says, in constructing relativistic GRW type theories, people use a Dirac multi-time wave function to take care of the energy dispersion and the unique time variable in the wave function. The remaining challenge is to implement the collapse using only relativistic space-time structure. This was first successfully achieved in, so this means relativistic GRW with the flash ontology. The theory specifies the joint probability distribution of all future flashes where the initial conditions are a wave function defined on an arbitrary space-time slicing and a seed flash for each particle. And so that kind of looks like this. So we have our particle 1 here. We can think of this as our seed flash. This is the future cone for it, and we have this probability distribution on a future hyperboloid. So given this seed flash, we can then have a probability distribution of future seed flashes on hyperboloids that go inside of the future light cone there. So instead of universal time, one takes hyperboloids foliating the interior of the light cone of a seed flash. So that's what I have shown right here, which assign a proper time to each event. The hyperboloid structure also defines the collapse mechanism as one specifies a Gaussian function relative to it. So instead of specifying a Gaussian wave function on just a slice of space-time, it is now on a hyperboloid foliating the future light cone there. This theory is non-local. For two particles in an entangled state, the collapse associated with a flash on one particle can change the probability distribution for the flashes of the other particle, regardless of their space-like separation. So that's what we're showing here. We have this particle here, and doing something to it, say a measurement, can change the probability distribution on the hyperboloid of the other particle right there. People have also proposed relativistic GRWM, a Lorentz invariant collapse theory where the matter density ontology is defined at each point with respect to the past light cone at that point. So now it has become relative time translation invariant, as it is Lorentz invariant and foliation free. This theory is also non-local for similar reasons to the one we were just talking about. There is no relativistic GRW particle theory yet. However, there seems to be no reason to believe that such an extension cannot be constructed. So although the stochasticity of GRW allows it to work in a relativistic space-time structure, Allery 2022 points out that this comes with its own costs in terms of causality. So she says, nonetheless, in relativistic GRW type theories, we have more than a violation of the principle of uniformity of causation. In fact, in GRW type theories, the distinction between cause and effect, as we commonly understand it, seems to vanish, so that this principle does not even apply. To see this, consider an EPR type of experiment and pilot wave theory. Since there is a preferred foliation, the settings on the side which measures first can be thought of as influencing the outcomes on the other side. In contrast, because of the stochasticity in GRW type theories, cause and effect can be thought of as symmetrical. Nothing can be regarded as the cause and the other as the effect in an obvious way. In fact, by no longer having continuous world lines for the primitive ontology, for instance, making the ontology discrete in both time and space, as in GRWF, or having the primitive ontology jump, like in GRWM or the GRW particles, or in general by having the wave function jump in theories without a primitive ontology, it is difficult to say in what sense an event has caused another. And so she says, anyway, it is important to notice the following. Whether or not one can make sense of stochastic explanations, the fact that in GRW type theories the notions of cause and effect become symmetric threatens the very idea of influence. In fact, how can we make sense of the notion of influence if we cannot even identify which one is the cause and which one is the effect? While it is true that Bell's definition of local causality is applicable to stochastic theories, as obvious given by the way that GRW type theories are non-local, still the intuitive notion of locality it is supposed to capture in terms of cause and effect is gone, and this should be recognized. One could argue that there is still room for the notion of cause and effect, at least in some frame relativistic sense. In fact, one could argue, take an EPR experiment where Alice measures her particle first. Her doing that can be seen as the cause of the result of Bob's side. However, in reply, notice that in relativistic GRW type theories, there is a perfectly legitimate frame in which Bob performs his experiment first, and thus it will be his measurement to be the cause of the result on Alice's side. In other words, there are frames in which one event is the cause and frames in which the same event is the effect. Since there is no privileged frame, these frames are equally legitimate, and thus cause and effect have no absolute meaning. So we can think about it this way. We have Bob right here making his measurement first, so his ends up as spin up. Alice is not yet in a definite spin state, but as soon as hers ends up in the past, it will be in a definite spin state caused by Bob's. Or we can have it the other way around, where we have this perfectly legitimate frame of reference here, where Alice's is measured right here. Bob's is still in a superposition until his ends up in the past light cone, and so his will end up in a definite spin state, and that will have been caused by Alice. And so we get this symmetry here where we can have Alice or Bob be the cause of the other one's outcome in their measurement. And so Allery 2022 continues. In GRW type theories, the interaction notion of locality is completely lost. This goes beyond what happens in the pilot wave theory, as effects always follow their causes. Instead, implementing relativistic spatiotemporal structure with stochastic laws as done with GRW type theories seems to get local influence entirely out of the picture for the reasons we have just seen. This has an important consequence. If the original idea for considering GRW type theories was to find a way in which quantum mechanics and relativity could peacefully coexist, then while these theories are relativistic in the sense of respecting relativistic spatiotemporal structure, they leave little room for the other spirit of relativity, namely the locality of interaction. And further, GRW theories have what Allery calls super non-locality, which means non-locality with a single particle. So consider an experiment with a single particle confined in a box. Someone inserts a barrier in that box, thus splitting the particle's wave function in two. The two half boxes are then separated, at which point one of them is open. According to the pilot wave theory, in such a situation, the particle is simply in one of the half boxes the entire time. In our relativistic GRW matter field theory, given it is only one particle, no wave function collapse has happened, and the matter density is half in one half box and half in the other. So that's what I'm showing up here. So we have this box, we split it in half. Its matter is split between both of these half boxes 50-50. Suppose now someone opens, say, the half box on the right. The particle gets coupled with the measuring device, and the wave function most likely collapses. That is, the matter density all jumps in one of the half boxes. Since the process is random, either the part on the right jumps to the left, so we have it sort of half here, but it all jumps to the left, so it's 100% in the left, and so then nothing is found opening the right half box, or it all jumps to the right, and the particle is found in the right box. In both cases, there is non-local matter transfer, even with one particle. Nothing like this happens in the pilot wave theory, hence the name super non-locality. To see non-local effects, one needs at least to have two particles, while here we only need one particle. In GRWF, given the discrete nature of the ontology, there is nothing in both half boxes until someone opens one of them. So I'm showing these as empty because our particle is purely in configuration space, but then once somebody opens one of these boxes, we see we end up with a flash in one of them. And because of this, she concludes, however, I think that similarly to what I have emphasized above in the case of stochasticity, super non-locality seemed to undermine the whole motivation for GRW type theories. In fact, someone may be attracted to GRW type theories to get quantum theory and relativity closer in the space-time structure first approach. However, again, since these theories are super non-local, they get quantum theory and relativity further apart in the other spirit of relativity, namely with respect to locality of interaction. In other words, if the idea is to find the best balance between the various sense of relativistic theory, locality of interaction, and relativistic space-time structure, then relativistic GRW type theories may gain the latter but lose the former. Because of this reason, I believe that the alleged advantage of relativistic GRW theories in respecting relativity rests on shaky grounds. And she summarizes this thesis by saying, within our current understanding, it is like genuine relativistic invariance is a blanket which is too short given quantum non-locality. If you manage to make a theory as local as possible in the sense of the interaction, then you lose relativistic space-time structure, like in relativistic pilot wave theories. While if you preserve the relativistic space-time structure, then you lose all locality you could have left in the interaction, like in relativistic GRW type theories. In other words, relativistic pilot wave theories have a preferred frame, which is against the relativistic spatiotemporal structure, but they are as local as possible in the sense that the interaction is not super non-local. Relativistic GRW theories respect these relativistic spatiotemporal structure by making cause and effect symmetric, but they end up giving up on locality of interaction entirely, as also shown by their super non-locality. And so what that means is that there seems to be a trade-off here where you can have this sense of locality, but then you lose that space-time structure because you have to have a preferred frame of reference, or you can give up the preferred frame of reference, but then you have to give up on things like cause and effect. And so there seems to be kind of a dilemma here. And in fact, some of the other papers, which I do have linked to in the references here, they talk about how this issue seems to kind of make us have to question what we even really mean by relativistic. But anyway, that was everything I wanted to talk about in this video. I hope you found that interesting, and I will see you in the next one.